Good afternoon, everyone. And welcome to this first lesson of digital signal processing. Okay, we already know each other, so I'm gonna skip the presentations. A quick announcement before I'm starting talking about the first topic. The syllabus is still not on the Moodle. It should appear in the next days, hopefully. So let's keep it optimistic. However, you should know that until further notice, the content of the course is similar to the one that was in the previous year. So people who want to know what awaits them can download the syllabus from previous year in Hebrew and can look at it. Okay? So the first thing I'm going to talk about today is the classification of discrete time signals and systems. This is merely a review class. Okay, it's going to be very boring because this is stuff you know already. So I'm going to go over this a bit quick. Okay, so let's start now. Okay. So this is an introduction lecture, and I'm going to talk mostly on the definitions that you know already from the previous course, signals and systems, like, causality, stability, linearity for systems, and periodicity for signals, and stuff like that. Okay, so it's going to be something you know already, so it should be, at least in the beginning, it should be easy. If time allows it, I will finish with some additional definitions that do not exist for analog signals or for analog filters. Also, a quick remark before I'm diving. I will use the term filter or the term system equivalently. Okay, please know that we are talking about the same thing, the exact same thing. And just so you start practice your English as well. Well, in the previous class, I said that an analog filter is like it's an electronic filter. So, okay, so it's made of capacitors, inductances, resistors, and you name it. What could be a digital filter? What is a digital filter from an engineering point of view?
Gates, like or not?
No, because this is also some kind of semiconductor thing. And we're looking at, you're looking at it from the practitioner side, okay? You're not going to program the gates themselves.
Op amps,
Hmm?
operational amplifiers.
No,
They
that's
convert.
electronics.
Hmm.
So the answer to this question is that a digital filter from your side, sorry, there was another tentative answer here.
I thought breakers, maybe.
Sorry?
Breakers, maybe?
No, not much. We're not talking about anything physical. I mean, the answer to that is that a digital filter is a piece of code. Okay, that's a code running either on a computer, either on a processor. This code can be either written in C language, in VHDL, in MATLAB, in Python. It doesn't matter really, okay? We're talking about the processing of digital signals. So we're talking about the processing of something which has been digitized, which has been stored inside a hard drive, okay? So a digital filter starting now is a piece of code. It's a program, okay? So it means that it changes also all the engineering conception, okay? Because for example, if you want to design an electronic filter, then you want to choose the components accordingly, and you want to choose as few components as possible. So the price for analog systems, that is the main bottleneck. When we're talking about a digital filter, the main bottleneck is not the cost, the overall cost of the signal, of the system, because it's a piece of code. And besides the time invested by the programmer, it does not cost anything to maintain it. So here, the main bottleneck will be the execution time. We want something that runs efficiently, obviously, but we want something that runs fast. Okay? So I'm not going to talk about complexity of the algorithm because this is computer science and we do not have time for that. But there will be a lesson about FFT, about how can we improve the code for computing the Fourier transform and making it more efficient. You've been warned. Okay. Okay, that's administrative stuff. This is my email. We can convey reception hour by email using Zoom. Office hours are in the syllabus that will be published, but I will remind them now. We are talking about either Thursday from 9 to 12 or immediately after this lecture. And we also have Tuesday, which is from 2 to 4. Again, I have no objection doing reception hours using Zoom, but this will be done independently and individually. So we need to fix the appointments. Okay. So what I'm going to talk about during at least 9 lectures is the basic tools, basic theoretical tools of digital signal processing. I'm talking about the Z-transform, the DTFT, the FFT, the subsampling, and oversampling. This part of the course, this is the theory, okay? And it will keep us busy most of the semester, okay? I think 10 weeks, give or take, okay? But it depends on it depends how you react to the English, okay? If we see that we need to slow down a little bit so that you can understand better, then it might take more than that. And in that case, I will take time from the applications that I'm going to talk about. Classically, we have 9 to 10 weeks of theory and 3 to 4 weeks of application, where the main application that we investigate is designing the FIR filters and the IIR filters. So far, we do not know what FIR means or IIR means, and that's perfectly okay. I'm going to talk about this at the end of this topic. Okay? So what do we need to know to pass this class? Well, obviously you need to know the previous requirement, okay, signals and system, that is mandatory. It will greatly help if you know how to manipulate complex numbers with ease, okay, because I'm going to make lots of calculation with complex exponentials, and I'm going to make lots of simplifications on these numbers. So if you can go over the material of complex functions at least once, that could be super nice. How is it so far?
Good.
Okay.
Will you be writing as well, or it's just presentations?
Well, I will be writing on the slides, okay, when I want to say something. I think, well, this is my. I don't mind making a full written class, but I have the feeling that it will be more difficult to follow. So I think that what is best is to write at least part, non-negligible part of the course in English, and then add some things in written in the slides. And I can upload the updated slides with the writings afterwards.
Thank you.
Now, where is? All right. So as I said, DSP is digital signal processing. Okay, so digital signal processing, the most important word in this term is obviously the term digital. Okay, it's not a surprise for you. Okay, we're living in the digital age after all. So it's perfectly clear that most of the engineering operations that you're going to do on physical phenomena, they're going to do on a computer. So this is the important part. It does not contradict the fact that the physical phenomena that you're dealing with, they are analog by their own nature. Okay, so a typical pipeline would be something like this. Okay, let's say for the sake of the argument that I want to record my voice. Okay, so this is the guy speaking, and he's talking or shouting, I don't know. Okay, so basically the voice is an acoustic wave, and this acoustic wave goes into a microphone, and this microphone converts the acoustic wave into an electric one. Okay, and let's say that you want to analyze or you want to process this piece of voice. So far, we are in the analog world. Okay, everything here is analog. So the first step would be to convert this voice to something digital. This is done using an A to D converter. Okay, this converter, it includes two main operations. The first one, you know it already. You're sampling. You're sampling your signal at a sufficient rate. Okay, and the second operation is a little bit less known. Okay, you're normalizing everything. I'm not going to talk about it for the moment. Okay, but let's say that at the end of the day, you have your typical digital signal, which is a vector. Graphically, I will represent it as a sequence of real values, where the index here is the place in the vector, and here on the y-axis, you have the value of the nth element in the vector. Okay? So let's say for the sake of the argument that the value are 1, 2, 1.2, and 1.8. It means that your digital signal is a vector whose values are 1, 2, 1.2, and 1.8, etc., etc. Okay, obviously we're talking about a longer signal. And that's it. This is a discrete time signal. A digital signal is something a little bit more technical. It means that the values themselves, they are also sampled. It is digitized, okay? So xn along the semester, that's a discrete time signal, okay? Digital signals involves the quantization of the values. It introduces some theoretical complexity and practical complexity. So I'm not going to talk about it in this during the semester, but obviously this is a practical, the practical one. Okay. Now we're taking this vector. We are coding our filter using MATLAB or Python or whatever you name it. And we provide in the input of the digital filter this discrete time signal, x of n, and we get another signal y of n, which is a processed version of xn. Let's say that we removed the noises or we filtered the voice, you name it. Okay? And if for some reason I want to listen to my filtered voice, then obviously I will need to move back to the analog world using a D2A converter. Okay, so we'll get some kind of analog signal here. And that would be, let's say, a full pipeline. All right.
Tom,
Yep.
how similar is the Y with the wave on it to the original?
It depends on what you put in your digital filter. It means that if you want to remove the noise, it might be slightly different because removing the noise out of a speech signal is a difficult process. If we're talking about encrypting the signal, then it will be very, very different. So basically, it depends on this block here. Incidentally, I know I have to talk in English, but you are not obliged to ask anything in English during the last 10 minutes, okay? In the meanwhile, if you want to ask something during the lecture, please ask it in English for the currents, because it is a bit difficult to switch from the English to the Hebrew to French, from Hebrew to English. So it's a bit challenging. Okay, so the most of the class is here. Okay, the digital signal processing world, that's all of that. So obviously I'm going to talk also about the A to D and the D to A, because inside these blocks there are interesting there is interesting stuff going on. And also I have to talk about frequency conversion, because when you convert from one sampling rate to another sampling rate, also problem appears. It's all related to these sampling applications. So we're going to talk a little bit about the A to D and the D to A, but that's not the main issue. Okay, the main volume of the class is about investigating these discrete time signals and designing those and analyzing, obviously, those digital filters. Okay, so what is the discrete time signal in that case? So as I said before, discrete time signal is merely a sequence of values. Okay, pay attention to the brackets here. Okay, these brackets means that you're talking about a discrete time signal. When you're using the regular parentheses, we are talking about continuous time signal. All right.
Discrete meaning singular, like separate singular.
No, discrete, it means that if you need to represent the signal graphically, okay, your x-axis is not continuous, okay? For example, let's say that I want to define the discrete time signal as follows. Okay, 3n plus 2. So it means that for n equals 0, the value of the signal is 2. For n equals 1, the value of the signal is 5. For n equals 2, the value of the signal is 8. Okay, etc. It means that between 0 and 1, there is nothing. Okay, Nothing exists. You have no value of the signal at 0.4 or 0.8 or at 1.3. It doesn't make sense, okay? It means that here we are talking about a discrete x-axis, okay? It means that the signal, the discrete time signal, is defined for integer values of n, and it is undefined elsewhere. Got it?
Mostly, yes.
But the x-axis represents time in either cases, right?
Well, not exactly, okay? It is homogeneous to time, but it's not exactly the time, okay? Let's take this 258 signal, okay? Can you reconstruct from it the analog signal that were used for its creation?
You'll
The answer
get
is no,
like
you
infinite.
cannot, okay? Unless I give you the sampling frequency. If I'm giving you the sampling frequency, then you might have a chance if the Nyquist condition holds, okay? But it means that in that case, n is not really homogeneous to time. It has no units, okay? Obviously, it is not completely disconnected from the time, okay? But it means that we need to talk a little bit further about it. So let's put it here. This is important enough. N is an index. It is related to time, but it has no value. It has no unit.
So I can refer to it as an array of values.
Yes,
Later,
that's exactly it. Okay.
Later I can convert it to time if I want to.
Yeah.
And could it be negative?
It can be negative. Theoretically, yes. Okay. Obviously, when you're programming, you start indexing your vector at 0 in C, in 1 or Python, or from 1 in MATLAB. Okay. But theoretically, you do not want yourself to restrict only to causal signals. So n is an integer. It can be positive or negative. Okay. Also, I would say that this is the direct definition of a signal, but considering that we are talking about a sequence of values, you could also define it the same way in a recursive manner. Okay. This is the same signal, exactly the same, okay, if you're starting from 0, but the signal is defined in a recursive way. Now, regarding those discrete time signals, you can define for these guys, similarly to the signal and system class, you can define the energy and the power of those signals. As you remember, at least as I remember, the energy of an analog signal is defined as the integral of x squared, okay? So we will use exactly the same standard for discrete time signals, but considering the fact that we're talking about a discrete time guy, so the energy will not be defined as an integral, but as a series, okay? So the energy of a discrete time signal is defined as it appears in the slides, okay, as the sum of x squared. We are adding here the absolute value to take into account also the complex valued signals, obviously. And if this is a finite value, we say that xn is an energy signal. Okay. In this part, I wanted to emphasize something that you know already, okay? In signal and systems, we said that if a signal is bounded in time and bounded in amplitude, then necessarily it is an energy signal. For discrete time signals, it is even easier because if you define a sequence, you need to attribute to each index a finite value. So every signal, discrete signal, which is bounded in time, is also bounded in amplitude. Okay? So
Can you repeat that, please?
yes.
Can you repeat it, Tom, please? You said if it's bounded in time, so?
Yes, I can. I said that if a discrete time signal is bounded in time. Okay, I did not recall what it means, but you get the picture, right? Something which has zero values and then starts and then finishes and then is zero afterwards, something like that. Okay, if it is bounded in time,
Yes.
it is also bounded in amplitude.
Why exactly?
Because if you want to define it as in the previous slide, then I will go back to it. Okay, it means that for every n, you have to attribute a finite value. Okay, you cannot attribute infinity to an index. Does not make sense. Okay, a well-defined discrete time signal is defined for every index. It can tend to infinity, but it cannot be equal to infinity anytime. So if all the values are finite, and you say that it is bounded in time, so it is necessarily bounded by its largest value. So it is bounded in amplitude as well. So it means that all finite signals, let's say all signals in this framework, okay, in DSP, not in signals and systems, all signals bounded in time are energy signal. All right.
So we don't have the delta function like last.
Nope, we don't have it. We have a delta. This is the Kroneker's delta. This is not the Dirac's delta.
Okay.
Okay. So let's take, for example, something
Tom,
very
can I ask a
stupid.
question?
Yep.
You said that if x of n is bounded in time, but n is related to time. It's not directly time.
Yeah,
Like,
I know that the terminology is not very well chosen. Okay. It is bounded in time. I need to define it clearly. Okay. It is not exactly time. You're absolutely right about it. Okay.
it can be bounded in n axis.
That's the definition of it. Yes. Okay. Here, that's a good question, actually. You want to make the analogy between this DSP and this signal processing class that you had before. Okay. So if the definitions look similar, you will use the same terminology, even if it is not completely true. Okay. So for example, when I'm saying bounded in time, you're right, n does not represent the time. So I should say bounded in indexes or something like that. But considering that it is exactly the same definition than in signals and systems, then I will make this analogy and I will say bounded in time all the way. Okay?
Okay.
That's not a
But
big
there is no
logical leap.
There is
Hmm?
there is no situation that we are bounded in n-axis, but not really in time, right?
No. No,
Okay.
because if you take into account that this digital discrete time signal comes from something which was sampled at a given sampling rate, so it means that the signal, if Nyquist condition holds, it means that the signal after a certain time is uniformly equal to 0. So you don't
Okay.
have to worry about it.
Okay, thank you.
שאגבר לשאול בעברית, נכון?
Okay. Okay, so I'm gonna stop recording right now. I'm gonna make a quick. How do I say it? How do I do it? Yeah. All right. So now I'm gonna give some examples about energy signals. Okay, I'm gonna give 2 examples. One which is pretty straightforward. Okay, let's take this guy, which is equal to 1 when n is equal to 0, 1, and up to 2024, and 0 otherwise. Okay, so what we're looking at here, in a nutshell, it's a discretized version of the pulse. Okay, because we're talking about a rectangular pulse which starts from 0 and ends at index 2024. Okay. This signal obviously is bounded in time, so it is an energy signal.
Is that enough to write? If it's bounded in time, so it's energy. You don't need to say bounded in a, you can say that it's bounded in amplitude, but
Yes, but it doesn't bring any further information. So you can write it. It is not a wrong thing to write.
okay.
It's just a bit useless. Okay. And if I have to compute the energy, then obviously I will say, okay, then the energy of X is the sum of the values squared. But in practice, what's wrong with the pen? Something very strange happens here. Okay, it's
Like a magic.
okay. Let's try again. All right. So the sum from minus infinity to infinity, but in practice, this is a finite sum that we're talking about. This is a sum from 0 to 2024 of the values of X. All the values here are equal to 1 by definition. So we're summing 1 plus 1 plus 1 plus 1. And we get the finite value. Okay. Okay, the second example I'm gonna give is something like that. Let's take what will be the discrete equivalent of a damping exponential. Okay, so something like this. 1/2 to the power of n, if n is positive, and 0 if it is negative. So it looks like this, okay? For n equals 0, you will get 1. For n equal to 1, you will get 1/2, 1/4 for 2, 1/8 for 3, etc. So as I said before, this is the digital equivalent of a damped exponential, of decreasing exponential. Okay, so now this value So this discrete time signal, it is not bounded in time. So this time we have to make the full check all the way. We need to compute this sum. Okay, now the sum starts at 0 for obvious reasons, and it goes up to infinity. And in this range, the signal is equal to 1/2 by the power of n, and I need to square it, so it is 1/2 by the power of 2n. So it means that the energy, if it is finite, it is equal to the sum from 0 to infinity of 1/4 to the power of n. And now we all passed the calculus class successfully, so now we can say confidently, okay, this is a geometric series, and the inner term of the series has a radius which is smaller than 1. So I know that, because it is a geometric series, that this is equal to 1 divided by 1 minus 1/4, which means 4/3. 4/3 is finite. So this signal is an energy signal. Okay, at the end of
Why
this
is it
hour,
in
I
2n?
can. Sorry.
Why is it in 2n?
Why is it what?
In 2n, you said
You square
EX?
the energy.
Yes.
Yes.
Okay, okay.
Because of the
Sorry,
square
thank
here.
you.
Sorry. So at the end of the class, I will, if you need it, I can make a quick reminder about geometric series, because this series will be one of the main series coming during all the class. So we really need to know it and to master it. So please remind this at the end of the hour if needed.
Tom,
In any case, Ken, yes.
we need to do a convergence test. Use
No,
that?
for geometric series, you don't need that.
No, I'm talking about general series.
For general series, yes, a convergence test might be enough to check whether a signal is an energy signal or not, okay? But it will not be enough if you need to compute the energy explicitly, obviously. But if
Okay.
you're talking about Cauchy's test or D'Alembert test or any other test you're thinking about from calculus, yes, it can help.
Okay, thank you.
All right, so similarly, the power is defined like this. Okay, there's a mistake here, okay, because the power of a signal is the limit of this term when n tends to infinity, okay? It should remind you the term that was used to define the power for analog signals, and it is exactly the same, but instead of an integral, we have a series. And consequently, if this term, this limit, is finite, then we say that xn is a power series. All right? And similarly to the signal and system class you had before, okay, you can categorize your signals. Either they have a finite energy and then their power is equal to 0. Either they have a finite power but an infinite energy, or they have an infinite power and an infinite energy. So you can categorize these discrete time signals the same way you were doing for analog signals.
So the signal can be both power and energy.
No, cannot be both. That's what I said before. Yes, I need to add it that we're talking about a non-zero limit, but it is quite obvious because you're summing here positive terms. So if if the limit of this term exists, it is necessarily a non-null number. Okay? So no, you cannot be both. It is either an energy signal, either a power signal, or no, neither this nor that. Okay? Okay, so I'm gonna make a very quick example about power signal here. And we're gonna talk about the step function or the digitized step, something which is equal to 1 when n is positive and 0 when n is negative. Okay, if you're drawing it, so it is 0, 0, 0, 0, 0, 1, 1, 1, 1, etc. So this is mostly, we will denote it later on by u of n because this is the step function. Okay. So I want to check whether this is an energy signal or a power signal or neither this nor that. Obviously, if I'm looking at this term, okay, let's say from minus n to n. So in practice, these can be summarized as the sum from 0 to big N of the values of the signal, because for n negative it is 0. And considering the fact that all the values are equal to 1, so it means that this sum in practice is equal to n plus 1. So when n, yes.
Why did you use n and not infinity?
Because if I want to investigate the convergence, it is better first to look at the finite series, and then you let n tend to infinity, okay? And you check whether this limit is finite or not. It is exactly the same, okay? You could also, because if you're using your standard Cauchy or D'Alembert criteria, here you will get exactly 1 and you don't know how to conclude. So considering that the sum to infinity is actually the limit of the series from 0 to n when n tends to infinity, I'm computing the series from 0 to n, and then I'm letting n tend to infinity and look how it goes on.
Tom, the sum doesn't need to be 2 times xn squared, because for each negative value, you get the same value as the positive value.
No, because this minus n here, it is the range, okay? I'm summing all the values.
All right, from 0. All right. Yeah.
From here to there, okay? So this quick computation, what does it show? It shows first that when n tends to infinity, this series does not converge. So it means that xn is not an energy signal. But on the other hand, if I'm looking now at this term, I mean, the series I investigated before divided by 2n plus 1, then due to the computation I did before, I see that this tends to 1/2 as n tends to infinity. So based on this, I can say that x is a power signal.
Tom,
Yep.
can you repeat? I don't understand how we get the capital N plus 1.
Well, all the values of the signals in this interval are equal to 1.
Okay.
So basically, you're summing 1 plus 1 plus 1 plus 1
Yes.
n times.
Okay.
So the result is n plus 1, the number of terms.
Yes. Okay, good. Thank you.
Anytime. Okay. Well, this is
Tom,
all
do we
about.
have a third option?
What do you mean?
I mean, if it's not energy and not a power signal, we have something else to do, or
No. It means that it has neither a finite energy nor a finite power. So it is neither this nor that. You have 3 categories overall, okay? Finite energy, finite power, or and nothing at all, okay? So if both terms tend to infinity, then the answer is nothing at all.
okay, thank you.
All right. Something that probably Uzi talked about, okay, some common notations about signals which are used every time. First is the impulse signal, okay? As I told you before, this is not Dirac's signal, but this is Kronecker's data function. So it means that this is something which equals to 1 for n equals 0 and 0 otherwise. So as you can see in digital signal processing, the definition of the impulse is pretty straightforward, okay? This is a no-brainer at all. So for digital step, I told it, I defined it in the previous example, okay? So this is 0 for n positive, negative, and 1 for n positive. And similarly to the signal and system class, okay, we will put special emphasis on exponential signals. In signals and systems, in the previous course, exponential signals were defined like this. E by the power of st, where s is a complex number, okay? Now, in DSP, the definition is exactly the same, but for historical reason, we are noting that a little bit differently, but this is pretty much the same. We're defining exponential signal as z0 by the power of n, where z0 is a complex number. Again, this is a basic, this is exactly the same definition.
Could you repeat that?
Yes. I said that in signals and systems, for analog signals, the exponential signals were defined as the EST, as this one, okay? But for reason that I don't want to elaborate about, okay, in DSP, digital signal processing, the exponential signals are defined as Z0 by the power of n. Now, it is exactly the same because you can always transform Z0 using Euler's notation, and then you can go back to the notation that you know before.
So they also called as self-signals?
We will show later on, yes, that these are self-signals. We say eigensignals, actually, that's the exact term,
Okay.
for LTI systems, absolutely.
So Z0 is a notation for e to the power of s?
Yes, because s is a complex value, okay? So for example, let's say that you have e by the power of s like this, okay, without the t. So s, you can split it with the real part and the imaginary part, okay? And you have e by the power of s, ej omega. So
Yes,
here you will have the radius of z0, and here you will have the angle of z0.
Yeah.
Okay, so that's exactly the same notation. Okay, the reason we're not using the same notation along the way is purely an historical one, and like all history, this is very boring. Okay, so similarly to what we did also in the previous class, okay, we can invert. Sorry?
Could you go back for 1 second to the previous?
Sure, anytime.
Thank you.
Okay. So what I want to say here is that you can make the same manipulation on the free variable as you did before. Okay, you can almost. Okay, let's put it almost. You can invert the indexes to make what is a time reversal. See now? Okay, so let's say that if you have something like this for x, then the reverse version would look like that. Okay. But what I want to say in this slide is that you are not completely free to do whatever you want with the time index. Okay. For example, if we're looking at the translation by an integer parameter, okay, the important word here is integer parameter. If you want to translate a discrete time signal, the translation parameter must be an integer as well, because otherwise you will get out of the time indexes and your signal is undefined. Okay, so here n0 is an integer number. Okay, and similarly, you cannot define the shrinking operation and the stretching operation the way you want to. Okay, it is not trivial. Just so you can feel the difficulty here. Okay, let's say that I have this analog signal here, a nice triangle, and I want to compress it by a factor of 2. Then the graph of the compressed signal is pretty straightforward to draw. Okay, I have a triangle with a smaller basis, starting from -half to half. If I'm doing the same for the digital version of it, something like this, for example, and someone someone tells me, okay, I want to make a compression of this signal by a factor of 2. Okay, I have a pretty good idea of where this value and this value and this value, where they're gonna land. Okay, this one will stay in place, this one will go to 1, this one will go to -1. Okay, this I get, but what about the intermediate values? What about this one? Do I put it in half? It does not make sense. Do I discard it completely? I don't know really what to do with it. Okay, so I'm not saying that it is impossible for discrete time signal to define the shrinking and the stretching operation, but it means that we need to be a little bit more cautious. Okay, so we will dedicate for this operation a full chapter later on in the semester. So for now, I'm not gonna talk about it, and until a couple of lectures, okay, all the possible operations we're going to do on the free variables, they are inversion and translation with an integer parameter. All right. Question so far?
I might have missed your explanation, but do we use only discrete time in digital, or we have also the continuous?
No, we do not have continuous signal. Okay, For a, okay, just to say completely, okay, a digital filter is a program, okay? It's a piece of code. This piece of code will run on data that was saved in your hard drive. This data is digital, okay? So you do not mess with analog signals in DSP. Okay, so let's move on. Okay, those are a few properties that you know already. Okay, I just reminded it for convenience. You can see that these properties, they are more or less similar, okay, to the one you know from signals and systems. Okay, even signal if this equality holds, odd signal if I have a minus here. Those are the generalizations of the even signals and odd signals, okay, symmetric and antisymmetric. This is more or less known, okay? So unless there are any questions at all, I'm gonna skip it and pass to the next slide. Is it okay?
A is the symmetry axis.
Here it is the place of the symmetry axis. Here it is the place of the center of symmetry. Yes. And here, again, you do not have the full liberty of putting it anywhere you want, okay? It is either at a sampling point, either exactly between two sampling points, at the middle of it, okay? Yeah, okay. So now, based on what I knew for signals from signals and systems, I can also define a signal which is bounded in time, okay? It means that it exists in a finite interval and it is equal to 0 outside of it. I can define a right-hand side signal, a left-hand side signal, okay? Here I write it in Hebrew so that nothing is lost in translation, okay? This is Chasum Bazman. This is Tzad Yamin. This is Tzad Small, okay? And we will say that X is a periodic signal if there is N for so that the following equality holds. Okay, now quick question for you. Look at the last definition. Something is missing. What is the missing word in the definition before, in the last definition?
In the periodic, you mean?
Yep.
That the capital N needs to be a full cycle?
Well, it is the period, so it is a full cycle, but you need to precise a little bit more what you mean by that.
Hmm. That it needs to be a multiple of N?
It needs to be
Okay.
bigger than small
The
n.
smallest.
Okay, there are many things here that I need to complete. Okay, I think what you meant is this. N itself must be an integer. Contrary to analog signals, the period cannot be any real number you want, okay? You are confined to the discrete time scale. So it means that the period itself is also a discrete period. It is an integer. And what you, as I heard also, I will say that the smallest value of n such that this equality holds is called the fundamental period. Okay. So it looks like nothing happened here, but it means here that we need to be a little bit more careful, because we have this natural tendency to look at functions and quickly jump to the answer. The fact that a signal, an analog signal, is periodic does not necessarily mean that its sampled version will be periodic itself. Okay? So to conclude this hour, let's practice a little bit. Yes.
Maybe you already say that, but maybe I didn't notice, but the right-hand side can be also causal.
No, actually, I didn't say that, and it's good you mention it. Okay. In the definition of right-hand side and left-hand side, I made no assumption regarding the n0, its value. Okay, so you're right. Let's complete it. If n0 for a right-hand side is positive or equal to 0, we say that xn is causal. And if for the definition of the left-hand side, n0 is negative, then xn is what is called anti-causal. Thanks a lot for reminding me.
Anytime.
Okay, so now I'll give you a few seconds to copy that. And let's move to the planned exercise. Okay. Here you have
we
two
can
different
have
signals.
more second to copy this.
Okay, sure.
Thank you.
Okay, so now let's move back. Okay, we got two signals here. Two rely on the cosine function, which is a periodic function with period known, 2 pi. Nevertheless, the first signal is periodic and the second is not. Okay. So now let's deal with this exercise, shall we? X1 is defined like this. And as I said before, the cosine function by itself is periodic with a period of 2 pi. So it means that I can add 2 pi here anytime. So now let's move both terms together. And it goes like this. Okay, one, I factorized this pi altogether. So now if I'm looking at the definition of the signal and at this value, then I understand that x is actually equal to xn is actually equal to xn plus 8, which means
isn't there a pi missing?
No, it is factorized. Okay, so it appears both for here and both for here. No, it's okay. Thus, I claim that this first signal is periodic because it satisfies the definition. Okay, and considering the fact that I use the fundamental period of the cosine function in my calculation, I can say that the fundamental period here is 8. Now, the second example is going to be a bit more tricky, okay? Because I want to show that something do not exist. So it is a bit it is a bit more difficult. So usually, well, there is a Latin term to explain to give name to the demonstration. I'm not going to use it, but I'm going to assume that it is periodic, and I will derive some computations, and then we will get a contradiction along the way. Okay? So let's say that, just for the sake of the discussion, that x2, which is defined as cosine of n, is periodic. It means that there exists an integer n such that x2 of n is equal to cosine of n plus big N, something like this. What we know from calculus course is cosine is periodic with period 2 pi. So what does it mean about n? It means that it must be proportional to 2 pi.
Then it's not an integer.
No, n is an integer by definition because I assume that it is periodic. But it
Okay.
means that the fundamental period is unique. Okay, so if you're saying to me that n is a period and 2 pi is the fundamental period of cosine, so it means that both are proportional. Something like this.
But that will never be an integer.
Ah, now you get it. Okay, it means that here pi is equal to n divided by 2k, but it does not make sense. It does not make sense because on the right side, you've got a rational number. And on the other side, you know that pi is an irrational number. So they don't mix, okay? And since you've got your contradiction here, it means that your starting assumption was wrong from the very beginning. So x2 is not periodic. Okay, so I'm giving this example because it is very tempting when you look at both to say, okay, there is a cosine function, or there is a sine function, or there is any trigonometric function you want. I know that those functions are periodic, so the overall signal is periodic. Okay, well, this example shows you that this is not necessarily the case and that you need to be a little bit more careful. In a nutshell, okay, to make things very, very short, if you have a pi inside the trigonometric function, most chances are that the overall discrete time signal will be periodic. Okay, but anyway, you need to investigate it more carefully. All right.
Can you please repeat the last sentence you said?
I said if a rule of thumb here would be that if pi appears inside the cosine or the sine or the trigonometric function, there are good chances that this signal is periodic, but you need to investigate it carefully anyways.
Okay.
Okay. Okay, so far we went over the different properties of discrete time signals. Now it's time to talk about the digital filters or digital systems, name it whatever you want. Okay, so it's going to be very similar to what you learned before. Okay, we define basically a digital filter based on the input-output relationship. Okay, it means that to talk like a computer scientist, okay, this is the input program. T is the program itself, the sequence of commands that you're putting, and Y is the output of your program. Okay, so just to make the analogy complete, okay, I made here a small table, okay, to differentiate between analog systems and digital ones. So you can see here that a digital system, a practical analog system, is composed of electronic components or electric components, you name it. And when you're designing it, you focus on electrical laws because you need the full electrical laws to comprehend how the electronic circuit functions. And in that case, what you want to pay specific attention to is the cost of your electronic system. Whereas in the digital world, it's a complete different process because a signal, a digital filter is a software, okay? So the design is based on algorithmic considerations, whereas the critical factor here is the speed of execution. So it is good to keep this table in mind so that you make sense of what is written. But besides those differences, it is important to note that the definitions and the properties related to the digital filters are quite similar to the one that we encountered in the course Signals and Systems. So for example, I will say that a filter is memoryless, okay, בעברית רגעית. If I need only the value of the input signals at a specific time to know the output at this same specific time, okay? Otherwise, we will say that the filter has memory. So as an example here, I put here, okay? So the first filter, which is defined as 3 times x plus 2, is memoryless. Because if I want to compute y of 14, then I only need x of 14, and I know everything about it. Okay, the rest are like inner values inside the program, and it is not part of the input. But on the other hand, if I want to make the average of closed values, let's say to smoothen my signal a little bit, then this signal as this filter, as a memory, okay? Because I cannot rely only on x of 1 to compute y of 1. I need more than that. So the question here in this property is, do we need a buffer to store past or future value? Okay, so if the answer is no, then it means that your system is memoryless.
What did you write in the last sentence? In the
Do
left?
you need a buffer to store past or future values?
Past, all right.
Okay, because the memoryless property, it does not take into account the past or the future. It means, do you need some RAM to store your values? Or is it a real time? Sorry?
Can you repeat it?
Okay, I tend to speak a lot, so you need to be a bit more specific there.
About your last sentence.
Yeah, it means, do you need some RAM to store your value? Do you need some memory to store your values? Okay, it does not, I don't care whether these values are from the past or from the future. Do you need some place to store them to compute your output?
Okay.
Okay, a system will be called a linear system if the superposition property holds. Okay, it means that if I'm taking a linear combination of inputs, I will get a linear combination of outputs. Okay, this is a property that you know already. Again, you have the same shortcut if you want to check whether a system is linear or not. It means that if
NFS?
yes, exactly. Okay, a linear system with no input stays in the same state. So if a system is linear, then necessarily zero input gives zero output. So for example, if I'm looking back at the first example here, okay, if x of n is equal to 0, then the output is equal to 2. So it means that the system is not linear. On the other hand, the second system I investigated is indeed linear. So this is all for linearity, because this is, okay, this is obviously a known property.
So T of 0 equals 0 drags linearity.
Sorry?
T of 0 equals 0, it drags linearity.
No, that's exactly the other way around.
Other way
The
around?
linearity implies that T of 0 is equal to 0.
All right.
Okay.
It's only
But
one way.
if it's only one way, but you can look at it conversely. It means that if T of 0 is different from 0, then your system is not linear.
All right.
Okay.
So
Time invariance is defined. Sorry, again?
can you go back one page? Can you show us the solution to the second example?
Okay. Then I will need to move to something a little bit larger. Hold on a second. Okay, let's take it from here. Okay. So the system was defined as the average of two consecutive values of the input. Okay. So let's phrase it that way. Okay. Under the assumption that for the output, for the input, sorry, x1, I get y1. And also under the assumption that y2 is the output I get when I put x2 in the input. The question asked is, what is the output to, let's say, alpha x1 plus beta x2, okay? And we want to check if we get alpha y1 plus beta y2. Okay, so let's do it. We provide in the input alpha x1 plus beta x2. So let's look at the equations at the equation above, okay, the one defining the system. Okay. So if I'm reading this equation, it is pretty straightforward. The output is equal to the input plus the translated input divided by 2. Okay, so I will apply this on the new input. As I said, the input plus the translated input divided by 2. Okay, and then you're gonna rearrange the terms like this: alpha x1 plus x1 n minus 1 divided by 2. Okay, I'm taking the first term and the third term all together, plus beta x2 of n plus x2 of n minus 1, also divided by 2. This is done by combining the second term and the fourth term. Okay, so where do we go from here? The first term is indeed equal to alpha t of x1. And the second term is actually equal to beta t of x2, which is alpha y1 plus beta y2.
Okay,
So
thank
the
you.
equality holds, so the system is linear. Can I move back to the slide?
Yes, thank you.
Okay. All right. So this is about linearity. Now, time invariance is defined exactly the same way. Okay, a filter is time invariant if when I'm moving the input by a translation parameter, I get, and applying the filter, I get the same output as before with the same translation. Okay, this is exactly the same definition as before. So there are really no surprises there. Okay, so for example, the first system here is time invariant. The second is not time invariant. I'm going to do the first here because it includes a mathematical operation that you are not useful with. You are not there. You don't know much. Okay, so let's say that now I'm assuming that for x I get y, and I want to know what happens for the first system. Okay. What happens if I'm providing to the input the translated version of the original input? Then I get the sum from minus infinity to n of x. Okay, obviously there is mistake here. It should be k. Okay. Sorry about that. Xk minus n0. Okay. So now what needs to be done is something which is a bit unusual for you. I'm going to change the indexes inside the sum. Okay. So it is exactly the same, mental manipulation as the change of variables inside an integral. That's exactly the same. Okay. So I'm going to define a new index, which is k minus n0. K tag is equal to k minus n0. when you're making a change of variable inside an integral, you change three things, okay? You change the integral's limits, you change the term inside the integral, and you change the dt or the dx or the du, whatever you name it. So for series, it is even more simpler because you only change the inner term and the limits of the sum, okay? So when k tends to minus infinity, k tag also tends to minus infinity. And when k equals n, then k tag equals n minus n0. And then eventually, the inner term is transformed to x of k tag. Once you get there, this is pretty straightforward because this sum, it is exactly y of n minus n0, which shows that the first filter is time invariant indeed. Okay, so again, when you want to perform a change of variables inside a series, you can do it, okay? But you need to change the limits of the summation and you need to change the inner term accordingly.
Is n0 also an integer?
N0 is also an integer because we said that the translation parameter must be an integer.
Tom, can you explain how does it equal to y of n minus n0?
Well,
Just the last part.
because if you want to compute, let's take a numerical example first, okay? Let's say that you want to compute the output for n equals 0. Then in every place where n appears, you will put 0, okay? So if I want y of 0, I put 0 here. That's it, I got it, okay? If I want the value at 9, then I will put here the sum from minus infinity to 9. All right? So now let's say that I want to compute the value at the general index, let's say m. Then everywhere n appears, I will replace it with n. So now look at these two sums, this one and this one. They are pretty similar, right? This is exactly the same sum. This is the same series, but the upper limit here is not n, it's n minus n0. It does not bother me because I said, okay, this term is equal to y of n. So this term is equal to y of n minus n0.
Oh, okay. Thank you.
Okay, regarding causality, the definition is similar, okay, to the one you know. We will say that a digital filter is causal if the calculation of the output at a given index depends only on the past indexes of the input. So here I give you a few examples. Okay, the first system is causal, the second is not causal. I leave this to you as an exercise. That's a great exercise. By the way, let's say that you have the same property that I didn't put it because it's, well, it's not very used, but we said in signals and systems that a system which is memoryless is also causal. So we can put it here also. If a filter is memoryless, it is causal. It does not mean that all causal systems are memoryless. Okay, for example, the filter that you're seeing right now, the first one, it is causal, but it is not memoryless.
The second one is not
No,
is it
it's
causal
not cause. It's
because
not
the
cause.
square?
Okay, let's think about it a little bit. Okay, let's say, for example, that you want to compute the value of the output for n equals 2. Okay.
Okay.
So if I'm looking at the equation, it means that I will need to compute the summation from 0 to 4. Okay.
Yes.
So let's wrap this up. To compute y of 2, I need x of 4. So that contradicts the definition of causality.
Okay.
All right. Stability is defined exactly the same way. Okay. A filter is stable if for any input signal which is bounded in amplitude, the output signal is also bounded in amplitude. Okay. Here I give 2 examples. This is pretty straightforward. If you want to go at the end of the class to go over some of those examples, we can do it. But I need to advance a little bit. So let's continue. Okay, and similarly, I would say that a filter is invertible or reversible if the input-output relation is one-to-one mapping. Okay, so it means that for any existing output signal, I can find a single input signal which corresponds to it. So here, for example, this filter is invertible. It's not straightforward, so it's a good exercise as well to check this. And Y is not reversible.
Does invertible and reversible, is it like interchangeable? It's the same term? It means
Yes,
the same thing?
yeah, it means the same thing.
Okay.
Okay. Invertible is the more formal way to define it, to be honest. But everyone will understand you if you're using both terms.
Okay, thank you.
Okay.
Tom, can I ask a question?
Yes, sure.
We said that if we get a discrete signal that is bounded in time, it's also bounded in amplitude, right?
Yes.
So if I get a discrete signal that is bounded in time, so I can say that it's the last definition. How do you call it? Can you go back?
Yeah, sure. Stability?
Yeah. So can I say that it's stability?
No. Because it must hold for every signal, not only the one which are bounded in time.
Oh, okay.
All right. So let's proceed. Well, we will put a particular emphasis to LTI filters along the class. Okay, I recall that we're talking at linear and time invariant filters. Okay, I'm just reminding this, but this is obvious for most of us. LTI stands for linear time invariant. So an LTI filter verifies both properties. Okay. And again, we can define the impulse response of this LTI filter as the output that the system provides if I put the Kronecker's delta function as an input. Okay. As I said last year, okay, you can always define the impulse response for any system you want, but this is only important for the LTI filters, because in that specific case, again, you can claim that the output of an LTI filter is given by the convolution between the impulse response and the input signal. Here I'm talking about the discrete convolution. Okay, so it is the exact definition, the exact same definition as you know, but with a sum instead of an integral. Do you have any questions on that, or is this known to you? Or is
This is good.
This is good. All right. So let's proceed. Okay, this is the. Okay, let's skip the demonstration. If you want, I can do it. I just want to remind you a few properties of the discrete convolution and add some extra ones which can be interesting in the digital framework. Okay. Okay, so first of all, commutativity. Oh, the discrete convolution, I summarize it with a sentence. The discrete convolution has the same properties exactly as the continuous one. So to summarize it, okay, commutativity means that X and H are interchangeable. You will get the same result in the left or in the right. Associativity talks about where do you start your computations, but if you're starting from the beginning or from the end, you will get exactly the same result. Okay, and distributivity means that if I make the convolution between a function and the sum of a function, then it is exactly the same as doing two convolutions separately and sum the results afterwards. Okay, to these known properties, I would like to add two additional ones. Okay, they are pretty straightforward, but it is interesting to notice because it gives also an additional way to compute convolutions in practice. So here it comes. Okay, this is a basic reminder. Okay, when I'm doing a convolution between X, let's say signal, and delta Kronecker, what do I get?
The same signal, X.
The same signal, exactly. Right. And when I'm doing a convolution between a translated version of delta Kronecker,
Translated X.
0.
Yes. So this computation rule, we know them already. You saw them for Dirac's function. It is the same for Kroneckers. But here it is quite useful because it helps us compute convolutions in an easier way. Okay. Let's see if I don't have it here. So let's move back to the sheets and try to talk about it. Okay. Let's make a very quick exercise. Let's say that I have two signals, something like this. And something like that, something uniform between 0 and 3 and 0 otherwise. And the exercise will be super easy. let us compute the convolution between x and y. So how can I do it? There are many ways to compute this convolution. Okay, I'm pretty sure that you will see with Uzi additional methods to do it. You can do it in the time domain. You can do it in the frequency domain. It's all good. And in contrast to analog systems, here you have an additional method. First, just so that it is clear to everyone, I will draw both of them. The first graph represents x of n. The second graph represents y of n. Okay. So my claim, it's not my claim, basically, this is a property which is called the shifting property, if you heard of it, is that all signal can be represented as a sum of translated Kronecker function. This is pretty obvious when I'm saying it, but let's say that it like this, that I can write xn this way, but I can also write xn that way. Right? This is the impulse at 0. This is twice the impulse at 1. This is thrice the impulse at 2. Is it understood?
Yes.
All right. So why is it interesting for me? Because in that case, what I can say is that the convolution between x and y is exactly the same as the convolution between these deltas and y. So based on the properties I said before, meaning distributivity and the properties of Kronecker's delta function with convolution, then I can say that this is equal to y convolved with delta plus twice a y convolved with the translated delta plus 3 times y convolved with the delta translated by 2. So it means that the convolution is equal to y plus twice translated y plus 3y translated by 2. And then the only remaining part is to draw this. So y is a pulse like this. Okay. Two y of n minus 1 is something like that. This is 2yn minus 1, and 3 times yn minus 2 is equal to that. 0, 0, 3, 3, 3, 3. what remains to be done now is to sum everything index after one after the other. Okay? So for example, if I want the value of the convolution, of the discrete convolution at 0, it is this value plus this value plus this value, 1. If I want the value at 1, it is 1 plus 2 plus 0, 3. Okay?
Tom,
Then,
can you repeat on the second graph?
which one?
The second one, the 2y and minus 1.
Okay. What's about it? I don't understand.
What about the n minus 1?
I translated the pulse on the right side by one index. So this signal is equal to 0 here, 2,
Okay, it took
2,
also
2,
4, yeah.
2, and zeros.
Okay, thank you.
Okay? Then for 3, you've got the value 6. For 4, you also have the value 6. For 5, you have the value 3. And for 6, and the indexes afterwards, you got 0.
Tom, you can explain what, how you know the value?
Sorry?
You can explain how you know the value? 6, 3, 6.
Well, I summed all of them. Okay, let's say that you want the value, let's say, give me an index, for example.
Tom, there's a way to calculate it with a 2x2 table, like we calculated the share distribution of two rolling dices. Can you show this method?
You could use it, yes.
Can you show it, or it's a secret?
Well, maybe after class I can show you, okay? Because this is not strictly related to what I'm teaching right now.
All right.
But in any case, okay? Let's say I want to compute the value of the convolution at 3, okay? For this index. Then I'm taking this value at 3, this value at 3, this value at 3, summing all of it, you got 6.
But how you know the value?
You know it because it was given y is equal to 1 all the way. So 2 times y is equal to 2, and 3 times y is equal to 3. So here you have 1, 2, 3. The sum is 6.
Ah, okay, thanks.
Okay, so it means that for discrete time signals, you have a very quick way to compute the discrete convolutions. Obviously, as long as the signal is finite in time, and it's pretty straightforward. Okay. Incidentally, you can see that when you're making a convolution between a pulse and that, and you get some a very strange shape. But if you remember the properties of the analog convolutions, the continuous convolutions, you know that the convolution has this tendency to stretch the results. It means that if one of the signals is defined in AB, and if the second signal is defined in CD, then the convolution is defined into A plus CB plus D. This will remember. So we will see later on that this discrete convolution, it shares the same property in the sense that you can infer the length of the input based on the input of finite signals X and Y. So I will talk about it in the next chapters, I guess.
Tom,
Question: the Fourier transform exists in the discrete signal?
Well, actually, you have like 3 different Fourier transform in digital time. You have the DTFT, and you have the DFT. And both are Fourier transforms. Both are express basically the spectral content of your input signal, but there are several differences between the two. So we need 2 chapters for them.
And another question, in the continuous signal, we saw that pulse convolution with pulse, another pulse, sorry, exact pulse, give us a triangle. This thing exists here?
Yes.
Okay.
And I leave it to you as an exercise. Know that you know the method, because it is exactly the same way to prove it.
Okay.
Tom, can you go back, please, to the
Sure.
slide before?
Sure. No problem. Do you see it now?
Oh no, I meant the convolution, the graph of the convolution. For a second.
This one?
Yeah, thanks.
Yeah.
All right.
Okay, guys. What I want to say. Okay. Now, regarding the characterization of causality and stability for LTI filters, you have the same criteria that you knew about. So let me remind them to you. For an analog LTI filter, you said that an LTI system is causal if and only if its impulse response is equal to 0 for negative times. And you said that this system is stable if the integral of the absolute value of the impulse response converges to a finite value. So in DSP, you will have exactly the same properties in the sense that the system is causal if and only if the impulse response is equal to 0 for negative values of n, and it will be stable if and only if the sum, the series of the impulse response converges to infinite value, is absolutely convergent. Okay. Now this is the demonstration of this, so I will leave that to your reading. Okay, and this, since I need a little bit more time, I will talk about it next week for the next lesson. And well, regarding this reminder, we pretty much covered everything. Okay, you see that there are very strong analogies between the course signals and systems and the course digital signal processing. This is for obvious reason. We are talking about the same field altogether. So obviously, if you go back to the material you learned during the previous semester, it will be easier for you to grasp the material. So for example, next week, we're going to talk about the Z transform. So if I'm telling you that the Z transform is exactly the same, it's the digital analogy to the Laplace transform that you learned during the 4th semester, then you understand that I'm going to talk about regions of convergence. I'm going to talk about the Z transform properties. I'm going to talk about difference equations and the block diagrams of filters and stuff like that. Okay. So for example, for next week, if you go back to the Laplace transform properties and the region of convergence from the Laplace transform, this can be super helpful for you. So I would like to encourage you to do that. And that's it for today. Thanks a lot. So now I'm going to stop recording.